इंट्रोडक्शन। आप सभी का कॉन्सेप्ट क्लासेस में दिल से स्वागत है। आज हम क्लास 12th के फिजिक्स के चैप्टर 1 इलेक्ट्रिक फील्ड और चार्ज को कंप्लीट करेंगे। वी विल ब्रेक डाउन एवरी कोर कॉन्सेप्ट यू नीड टू मास्टर दिस मटेरियल। Before we can calculate the forces between charges, we have to look at how materials handle them. Conductors allow electric charge to flow freely, while insulators block that movement entirely. If we bring a highly charged object near a neutral conductor without physically touching it, we force the internal charges to separate and migrate. Creating this electrical imbalance across a distance is called charging by induction. This animation demonstrates the formula Q equals NE, which defines the quantization of charge. You can count electrons as whole, distinct units, 1, 2, 3, but you cannot split them into fractions. Charges also follow two other strict rules. Additivity, meaning you can sum them algebraically, and conservation, meaning the total charge in an isolated system remains perfectly constant. Here we have a diagram showing 2 point charges, Q1 and Q2, separated by a distance r. To calculate the exact electrostatic force between them, we use Coulomb's law. The equation is F equals K Q1 Q2 over r squared. The resulting force increases with the magnitude of the charges and decreases significantly as the square of the distance between them grows. Watch what happens when we introduce a third charge, Q3, into the system. To find the total force acting on any single charge now, we apply the superposition principle. We calculate the independent force vectors between each individual pair of charges, and then add those vectors together geometrically to find the final resultant force. Direct force equations only describe interactions between specific particles. But a charged particle also modifies the space around it, creating an electric field. We define this field, E, as the force F experienced by a tiny test charge divided by the magnitude of that test charge, Q. It represents the invisible area of influence surrounding the source charge. This visualization shows the strict geometric rules that electric field lines follow. Notice their exact directionality. The lines radiate continuously outward from the positive charge and flow directly into the negative charge. They never cross each other, and their density indicates the strength of the field at any given point. In practical engineering, charge isn't localized to single points. It spreads out over objects. We map these continuous charge distributions in 3 ways. We use linear charge density, lambda, for one-dimensional wires, surface charge density, sigma, for two-dimensional planes, and volume charge density, rho, for solid three-dimensional shapes. This model illustrates an electric dipole, a pair of equal and opposite charges fixed at a specific distance apart, labeled 2a. We measure its strength using the dipole moment, P, calculated as the charge Q multiplied by that distance, 2a. The vector arrow for P strictly points from the negative charge to the positive charge. When you calculate the electric field generated by this dipole at a distant point on its axis, the geometry sets up the math. The observation point is a distance r from the dipole's center, making the distance to the near charge r minus a and the distance to the far charge r plus a. These measurements form the denominators in our field equations. In real-world applications, the observation distance r is massively larger than the tiny separation distance a. Because r is much greater than a, the a squared term in the denominator becomes mathematically insignificant. We drop it from the equation entirely, simplifying a complex fractional expression into a manageable formula. If we drop this rigid dipole into a uniform external electric field, the positive and negative charges are pulled in opposite directions. This opposition generates torque, calculated as Pe sine theta. As the rotational arrows indicate, this twisting force forces the dipole to physically rotate until it rests parallel to the external field lines. Here we see a flat plane being pierced by electric field lines, illustrating electric flux. To calculate this flux, we use the formula E dot A cos theta. The angle theta is measured against the area vector. Notice the glowing arrow pointing outward. The area vector is always strictly positioned at a 90-degree perpendicular angle to the surface itself. When we curve that surface into a closed shape, like this sphere wrapping around a charge Q, we apply Gauss's law. It proves that the total outward flux through any closed surface equals the total enclosed charge divided by the constant epsilon naught.
You do not need to measure the field at every external point. You only need to count the charge trapped inside. Let's test this geometric logic. We replace the sphere with a symmetrical cube, keeping the charge Q exactly in the center. Based on Gauss's law, what is the electric flux passing through just one single face of this cube? Gauss's law states the total flux for the entire cube is Q over epsilon naught. Because the charge is perfectly centered, that flux distributes evenly across all 6 identical faces. Therefore, the flux through a single face is exactly 1/6 of the total, or Q over 6 epsilon naught. This split screen shows our final complex shapes, an infinitely long charged wire on the left and an infinite flat sheet of charge on the right. Trying to calculate the electric field for these geometries using standard Coulomb's law requires difficult integration. To avoid integration, we exploit the symmetry of the shapes by drawing imaginary Gaussian surfaces. We wrap a cylinder around the linear wire because its field points strictly outward in a radius. We intersect the flat sheet with a cylindrical pillbox because its field shoots out in parallel lines. Matching the boundary to the field's symmetry makes the angle constant, reducing advanced calculus to simple algebra. This grid presents every formula derived in this chapter, organizing Coulomb's law, field equations, dipole torque, and the Gaussian applications. Pause the video and take a screenshot now. Keep this sheet open beside you as a reference guide while working through your practice problems. अगर वीडियो अच्छी लगी हो तो लाइक सब्सक्राइब ज़रूर कीजिएगा और अपने दोस्तों को भी शेयर करो ताकि उनको भी हेल्प मिल सके। थैंक यू। तो मिलते हैं अगली वीडियो में। तब तक के लिए ओके बाय।